As you could kind of tell on the last slide, doing these with a circle is kind of a pain in the butt. The pictures can be really confusing. So what we use is called an energy diagram. So the bottom down here is the place of the lowest energy. So you can think of that as, I always think of it as kind of close to the nucleus. I mean, it physically is. Anywhere you go up, you're going to go higher and higher and higher until you get up here, and this line we'd call the ionization line. So like if you get more energy than up here, the electron is free. Yay! Photoelectric effect. Electrons flowing. Life is good. But we don't care about that for these problems. All right, so let's just give an example. Let's say we had an electron and its natural state was kind of here at 2, is doing its thing. And along comes some electricity, some light, something excites it. Whee! And it goes up to a higher state. And then sadly, it's going to have to come down. So here it comes back down. Oh. Okay. All right. How much energy, what was that change in energy like? Okay, so we have our change in energy. It's final minus initial. So our final was negative 3.4 electron volts minus our initial was negative 1.51 electron volts. So our change in energy is negative 1.89 electron volts. Now, where did that energy go? Well, it came bombing off here in the form of light. In other words, a little photon with this amount of energy was released. So now we got a photon charging through the universe with a charge of with the energy of 1.89 electron volts. How would a human experience that? Well, electron is going to be equal to HF, so E is equal to HF. Did I say electron? I'm sorry, energy is equal to HF. The H is Planck's constant. Which one you're going to want to use? We'll check out that EV. You're going to want to use the one with the EV in it, with electron volts in it. And we're going to solve for that frequency. So in other words, the frequency of light a human would see would be the 1.89 electron volts divided by Planck's constant electron volts, which is 4.14 times 10 to the negative 15th. Okay, so we divide that and we get a frequency of 4.5 times 10 to the 14th hertz. What does that mean? We don't often talk about color in hertz because it's annoying, but we can. If we wanted to get it in the more useful wavelength, we would use C is equal to F lambda. If I can stress anything, it's that if you know the frequency of something, you know the wavelength of something, because you always know the speed of light. So 3 times 10 to the 8th is equal to our 4.5 times 10 to the 14th. Oh my gosh. Times, Miss Story needs a nap. Times wavelength. And we get a wavelength of, let's see, apparently the devil's number times 10 to the negative 7th. So 6.67, I changed it to 10 to the negative 7th. And that's meters. So we're looking at 667 nanometers. Okay, and where would that be? Let's look at our little visual spectrum here. 667 nanometers. We go out here, boopy doopy doop, and we would be seeing something around here on our spectrum. So what you would really be seeing is, you would see that one little burst of light, and that would represent the little electron jumping up and falling back down. And what do you know? When you looked at hydrogen and you kind of broke it up with those glasses or something called a spectroscope, which does the same thing, you would see a band right here, this little red band, that would actually represent that jump happening inside of the electron. And you could go and look, and we are here in a second, we're going to go look at these other types of light here. These other types of light here, and we're going to see that those correspond to other jumps within the hydrogen atom. Okay, let's do another emission line. Let's just say that we're going to go have something originally was at 2, and it's going to gain some energy, absorb some energy, head on up to 4, and it's going to lose that energy. It's going to go back. So we're going to talk about that journey from 4 to 2. Okay, what kind of energy change do we go through? Well, originally, it's always final minus initial. So at the end of that transition, it was at negative 3.4, so it's final, minus the initial, which was negative 0.85. So E from 4 to 2, what we're going to see is the atom is going to give off negative 2.55 electron volts. Okay. So that's going to come off in the form of a photon bombing out like this. So what would that look like to us? We're going to go through and look at that. So the electron that's coming off is going to be 2.55 electron volts. Notice that we are losing the energy here, but that's what the photons got. So we're going to do E is equal to Planck's constant times the frequency. So we have 2.55, and that's in electron volts. So when we put in Planck's, we're going to want to use Planck's constant that applies to electron volts. So 4.14 times 10 to the negative 15 frequency, and then we're going to divide, and that gets us 6.16 times 10 to the 14th hertz. But now I want that in wavelength, so I'm going to use C is equal to F lambda. So if I want my wavelength is going to be 3 times 10 to the 8th divided by what I got here, so 6.16 times 10 to the 14th. And I'm going to end up with 4.87 times 10 to the negative 7th. In other words, 487 nanometers. And you can see when we go back to our original spectrum, that is this dude right here. So any of these lines are going to come from these different transitions that we see inside of that hydrogen atom. The interesting thing is you won't actually see with your eyes all of the different bands that are going to be coming off here, showing the different transitions. So what you are seeing when you actually put that diffraction grating up to your eye, you're just seeing this part. This is where the jumps between the energy levels are going to produce photons that come off in the visible spectrum. Over here, you see the jumps are much shorter. Because of that, there's going to be less energy coming off, longer wavelength, lower frequency. So you won't be able to see this because this is too low frequency. Over here, these big long jumps are going to produce a lot more energy, higher frequency coming off, which means they'll be too high. This will be in the ultraviolet portion of the spectrum. As atoms become more complicated, they add extra energy levels to their outside. So with those extra energy levels comes the extra ability to cause these different jumps. So you get more and more complicated models. Now, when you know that when you pass normal light through a prism, like normal sunlight coming in, you don't look at the wall and see emission lines. Instead, you see a broad rainbow. In fact, if you have a good enough prism and you organize the light enough, in other words, you make a thin little slit in a curtain and you pass it through the prism, you will see this whole rainbow. Except, just like Newton did hundreds of years ago, you will actually see big black chunks missing out of the rainbow. This is pretty cool. This would be an absorption spectrum. So we've looked at emission spectrum where electrons are jumping up due to excitement and then falling back down. And when they fall back down, they give up a photon. What we're going to look at now is the other situation.